This video is sponsored by Elastic and the Elastic Contributor Program. Now that we have covered term-level queries, it's time to talk about full-text queries, being another group of queries. Where term-level queries are used for exact matches on structured data, full-text queries are used for searching through unstructured text data. A couple of examples are blog posts, news articles, comments, etc. Think of full-text searches as entering a query into a search bar, such as on Google or within a mail application. In such a scenario, we surely cannot search for the entire content of a website or email, so we naturally search for specific words or phrases. That's what full-text searches are all about. Finding the documents that contain certain terms within unstructured text. Although not a requirement, these text values are often quite long, which is why we cannot feasibly perform exact matches on them. As you know, that's a job for term-level queries. Suppose that we have a posts index containing a number of blog posts. Here's one example of what a document looks like. The title and body fields are of the text data type. If we were to search for the word sharding, this document would match because it contains the word several times. That's essentially what full-text queries are about, finding the documents that contain one or more terms for a given field. Notice how I said contain, meaning that the field value doesn't necessarily have to be an exact match. In fact, that is rarely the case with full-text searches, because that's what term-level queries are used for. You can think of the field value as a haystack and the value we are searching for as a needle. Now that you know what full-text queries are used for, let's take a look at how they actually work. That should also make it more clear how they differ from term-level queries. One of the most important things to know about full-text queries is that the query is analyzed. Suppose that we are searching the body field for sharding. When processing the query, Elasticsearch will inspect the mapping for the field. If an analyzer is configured, it will use that one. Otherwise, it will default to the standard analyzer. The query will then be run through this analyzer in exactly the same way as when documents are indexed. The reason for doing this is that the values that are stored within the inverted index have been analyzed. To make sure we're not comparing different things, both values are analyzed in the same way. If this were not the case, searching for the word sharding in all uppercase letters would not match anything, because all terms within the inverted index were lowercased. Since the term we're searching for is analyzed, it matches the format of the inverted index. This analysis process is key to making things such as synonyms work, for instance. So, the query is analyzed with the field mappings analyzer. The resulting term is then used for a lookup within the inverted index. If there is a match, the documents containing the term are the ones that match the query. These are then returned as part of the query results. The fact that full-text queries are analyzed is also the main difference between those and term-level queries. Term-level queries are not analyzed and are therefore used for exact matching. Since full-text queries are analyzed, these are not used for exact matching. A bit earlier, I explained why term-level queries should not be used for fields of the text data type. For full-text queries, it's the other way around. They shouldn't be used with the keyword data type. That's because the values for such fields were not analyzed, but full-text queries are. Hopefully that makes sense. Before continuing, let's quickly talk about this video's sponsor, namely the Elastic Contributor Program. The purpose of the Contributor Program is to recognize and reward all of the awesome people who contribute to the Elastic community. This encourages and recognizes content creation and knowledge sharing within the Elastic community. By submitting your contributions, you are rewarded with points. At the end of each cycle, the top contributors are rewarded with cool prizes such as Elastic merchandise, free training, certifications, and more. And, best of all, you don't have to be an expert to contribute. Any contribution counts, whether it covers basic, intermediate, or advanced topics. Contributions can be pull requests, answers to technical questions, written content, videos, etc. Pretty much anything goes, so you will definitely find something that works for you. Be sure to sign up for the contributor program and start contributing right away. Check out the description below for more information. Thank you to Elastic for sponsoring this video. As for our first full-text query, we'll be using a query named match. The match query is the most widely used full-text query. It returns documents that contain one or more specified terms. The inner workings of it is basically what I showed you a moment ago, being that the query is analyzed and the result is then looked up in the field's inverted index. Let's type out a query that searches the name field for the word pasta. As you can see, the query matches 12 products, meaning that they contain pasta within their names. Just to reiterate, pasta can appear anywhere within the values, since we're no longer searching for exact matches. Just to show you that the value we're searching for is indeed analyzed, let's change it to uppercase letters. The results are exactly the same. What happened internally is that pasta was run through the standard analyzer, which contains the lowercase token filter. That's why both versions of the query searched for pasta in lowercase letters, which is also how the term is stored within the inverted index. Our current query only consists of a single word. We haven't really talked about what happens if we search for multiple words, something that's common within a search field. Instead of just searching for pasta, let's search for chicken as well. Before running this query, let's take a look at how this works. The value is analyzed in the same way as before, only this time the result is 2 terms instead of just 1. So how does this work in terms of the inverted index? Well, the short and simplified answer is that both of these terms are looked up to see which documents contain them. Let's run the query and see what the results look like in more detail. Scrolling through the results, we'll find products containing both of the terms, as well as ones containing just one of them. Let's take a look at why this is the case, i.e., why both terms are not required for a document to match. The match query actually has a parameter named operator, which controls the behavior of the query in situations where the analyzer yields multiple terms. The parameter is set to OR by default, meaning that a document matches if either or both terms appear within the field's value. If we explicitly set the operator parameter to AND, both terms are required for a document to match. Let's try that out in practice by making a copy of our query and then adding the parameter. This syntax we've been using thus far has actually been a shorthand syntax. Now that we need to add a parameter, we need to restructure the query a bit. In particular, the key containing the field name should have an object as its value instead. We then add a parameter named query containing the value we want to search for. And finally, the operator parameter. You can of course use this syntax without any parameters as well if you prefer, It's a bit more verbose, so that's just a matter of preference. If we run the query, we should only see documents containing both terms within the name field. And indeed that's the case. Those are the basics of the match query. It's one of the most fundamental queries in Elasticsearch, so chances are that you will use it for most of your full text searches. Don't be mistaken though, it's a quite powerful query, especially when using some of its advanced parameters, which we'll get to a bit later. As a last thing, I want to mention that you can also use the match query when searching for numbers, dates, and Boolean values. So if you have a search field, the query is pretty forgiving with anything you throw at it. If the search is not based on user input, then I do prefer to use term-level queries for these data types instead. But again, that's just a matter of preference. A moment ago, I ran a query that searched for both pasta and chicken. You can see the query and its results on your screen. As you know, a document will match if either or both of the terms appear within its name field. Did you notice, however, that the documents at the top of the results contain both of the terms? That's because there is an important concept that we haven't talked about yet: relevance scoring. Apart from the match query, we only covered term-level queries thus far. You might have noticed that the documents that matched these queries all had a value of 1.0 for the underscore score field. I just didn't mention it because relevance scoring is generally not relevant for term-level queries. That's because we are basically evaluating a condition that is either true or false. Either a document matches or it doesn't. There are exceptions, but this is generally the case. With full-text queries, however, we are no longer doing exact matching, so it's not just about whether or not a document matches. We also care about how well it matches. Consider the Google results for a search query, for instance. We surely expect the best results to be at the top and not on page 201. The same applies to full-text queries in Elasticsearch. Specifically, search results are sorted so that the matches with the highest value for the underscore score field appear at the top. In other words, the results are sorted descendingly by the underscore score meta field. This explains why documents containing both terms from the search query appeared first within the results. These were scored higher because they matched the query better than the documents that contained only one of the terms. Don't worry about the specific numbers that you see for the underscore score field. There are a lot of factors that are considered when calculating relevance scores, so it's actually pretty complicated. It's totally normal if you don't see the exact same numbers as me. We won't dive into how Elasticsearch calculates the scores now. For now, I just want you to understand how relevance scoring works at a high level. As you know, full-text queries are analyzed, and then the resulting terms are looked up within the inverted index for the fields. Nothing new here. Once Elasticsearch has looked up which documents match the query, it calculates relevance scores for each of them. When that's done, the documents are sorted based on the relevance scores to form the query results. Of course, that's not everything that happens, but that's a high-level overview. That's really all I want you to know about relevance scoring for now, so let's continue. You just saw the match query in action. That was great for searching a single field, but what if we want to search multiple fields? There are a few ways of doing this, one of which is to use a query named multi_match. That's what we'll look at now. The syntax is pretty straightforward, so let me just type out a query that searches both the name and tags fields for vegetable. Alright, no big surprises here. Let's run it and check the results. Quite a few documents match the query. If we take a look at the first document, we can see that the word vegetable appears within the name field. And for the second document, it appears within the tags field. Therefore, we were indeed successful in searching both fields at the same time. To be clear, a document matches if it contains the term for at least one of the fields. Now, that was easy, right? Don't be fooled though, because the multi-match query is actually a very advanced query, so let's take a look at what else it has to offer. A very useful feature is that we can adjust the relevance scoring. The way it works is that we can boost the relevance score per field to adjust the importance of fields. If a document matches the query for a boosted field, its relevance score is boosted by a number that we define. Consider the following example. A lot of products contain the vegetable tag, so products with the term within their name field might stand out as being a more significant match. If we want to boost documents where this is the case, we can apply a relevance boost to the name field. The way that's done is by specifying a caret symbol after the field name, followed by a number. To multiply the relevance score for such documents by 2, the query would look as follows. This effectively means that relevance scores are multiplied by 2 when documents contain the term for the name field. Running the query, we can see that the relevance score for the first document has indeed doubled. If you didn't pay attention to what the score was before, then I hope you'll take my word for it. Let's now take a look at how the multi-match query works. Elasticsearch actually rewrites the query internally to look something like this. As you can see, 2 match queries are constructed, one for each field. If at least one of them matches for a document, then that document will be part of the results. Technically, this is a slight simplification, but it's close enough. In terms of relevance scoring, this is where things get slightly more complicated. There is a type parameter that can be used to adjust how relevance scores are calculated. That stuff is pretty advanced, so I will just explain how the query works by default. If you need to adjust the relevance scoring differently, then I encourage you to check out the documentation. The default behavior is that the relevance score of the best matching field is used for the document. Suppose that we search the name and description fields for 2 terms, vegetable and broth. As you know, this query would be translated into 2 match queries internally. Within the first example document, you can see that the name field contains both terms, while the description field only contains the vegetable term. Without getting into the specifics, the Elasticsearch relevance algorithm gives the name field a higher score. That's the case for the 2 other documents as well. Note that these are just arbitrary relevance scores that I came up with, so don't worry about the specific numbers. By default, the multi-match query will evaluate the scores for each of a document's fields and take the highest one. In this case, that will be the ones for the name field. These relevance scores then become what you see for the underscore score fields within the search results, i.e. the document's relevance scores. The idea is that multiple fields are searched, but that the best matching field for each document is used. Once the relevance scores for all matching documents have been calculated, the documents are sorted by these values as normal. I do want to show you one way of adjusting this default behavior, with something called a tiebreaker. By default, multiple fields are searched, but only one field per document is taken into account in terms of relevance scoring. We might want to reward documents where multiple fields match. By defining a tiebreaker, we can incorporate all matching fields into the relevance scores for the documents. Let's take a look at an example to see how this works. In particular, the same query as before, but with the tiebreaker parameter. Within the example document, I added relevance scores for each of the two fields. As you know, the default behavior would be to select the highest one, being the name field, and use that for the document. With the tiebreaker, however, the behavior is as follows. The highest score is still selected, which is the name field. This gives us a score of 12.69. For every other field that matches, Elasticsearch then takes those relevance scores and multiplies them with our tiebreaker. For the description field, the 8.51 score would be multiplied by 0.3, which is 2.55. This number is then added to the best matching field's relevance score. The result of this is then the relevance score for the document. Here's what it would look like if we were to search 4 fields with 3 of them matching. Hopefully that all made sense. The point of doing this is that each document gets a relevance boost for each additional field that matches, besides the best matching field. That makes sense because if some of the terms appear in fields with a lower relevance score, this still signals some relevance that you might want to take into account. It might not always make sense depending on your use case. You might also want to tweak the tiebreaker to a different number. So that's about it for the multi-match query. Be sure to check the documentation if you're curious about the more advanced ways that the relevance scoring can be adjusted. A bit earlier we covered the match query. By default, a value matches if at least one of the specified terms appears anywhere within the field value. The terms may appear in any order as shown in the following example. Here you can see how searching for Fanta Zero and Zero Fanta will yield the same results. The terms also don't have to be adjacent as shown in this query that searches the description field. Let's now talk about phrase searches, which share many similarities to the match query, hence why I mentioned it. A phrase is a sequence of one or more words, such as browse the internet. In Elasticsearch, we use the match_phrase query to search for phrases. When doing so, the order of the words matters, which differs from how the match query works. Let's look at an example to illustrate the difference. First of all, the match_phrase query is analyzed in the same way as the match query, usually with the standard analyzer. Nothing new here. Let's go through a handful of example documents and evaluate whether or not they are matched by the query. Matching terms have been underlined for your convenience. Also notice that I'm showing the actual documents and not the inverted index. That's just to keep things a little simpler. While the first document does indeed contain all of the terms we're searching for, it's not matched by the query. That's despite the fact that they even appear in the correct order. The reason there is no match is that the terms are not adjacent, i.e. next to each other. Notice how there are 2 words in between the ones we're searching for, which is why the phrase doesn't appear anywhere. For a phrase to match, the terms must appear in the correct order and with no other terms in between. The next document is not matched either because one of the terms is missing and the order of terms is different. For phrase searches, it's a requirement that all terms are present, which is unlike the default behavior of the match query. Additionally, there are 2 other terms in between the matching ones. The third document also doesn't match. All of the terms appear, but they are not in the correct order. Note that the values that you see here would also be analyzed and stored within an inverted index. Therefore, the parentheses would be removed as part of this process, so these make no difference. If the terms were in the correct order, the query would match regardless of the parentheses or any other symbols that might be present. The next document does indeed match because the phrase appears within the field value. This means that all of the terms appear next to each other and in the correct order, matching the phrase that we are searching for. The same is the case for the last document, where the hyphen is dropped during the analysis process, exactly as the parentheses are for the third document. Alright, so how do these phrase searches actually work? How does Elasticsearch efficiently find the documents where the terms appear in a specific order? It's one thing to find the documents that contain the terms, but Elasticsearch also needs to keep track of where the terms appear within field values. I don't want to go into too much detail, because we'll look at this in a bit more detail later. But to give you a high-level explanation, Elasticsearch stores a bit more information within inverted indices than I showed you thus far. Here are two documents and the corresponding inverted index. This is how I have illustrated inverted indices thus far. However, this only contains information about which documents contain a given term, which is not enough information to perform phrase searches. Therefore, Elasticsearch needs to keep track of the positions of each term within documents. This information is actually recorded during the analysis process by default. When a string is indexed into a text field, the analyzer will record at which position each term occurred. Specifically, this task is handled by the analyzer's tokenizer. These positions are then stored within the field's inverted index as follows. For each document that contains a given term, the position of it is stored. Note that a term may appear multiple times within the same field value, in which case all positions are stored. This is just not the case for our two example documents. When running a phrase query, Elasticsearch uses these positions to check if the terms appear in the correct order. Consider the following query, for example. The query is analyzed as you would expect, yielding the following terms. First, Elasticsearch performs a lookup within the inverted index for the description field to resolve which documents contain the two terms. That's both documents in this example. Next, Elasticsearch needs to figure out if the terms appear as a phrase, i.e. next to each other in the correct order. That's basically just a matter of ordering the terms in the same order as within the query, and checking if the positions are in increments of 1. Based on the positions, it's easy to determine that neither of the documents contain the two terms as a phrase. For that to be the case, the positions of the term guide would have to be 3 and 5 respectively, i.e. one greater than those of the Elasticsearch term. Based on the term positions, we can also visualize the documents like this. As you can see, there are gaps between the terms for both documents, and they are also in the wrong order for the second document. That's just a different way of visualizing the same thing. Let's look at an example of a query that does match a document. First, here are two new example documents, along with the corresponding inverted index. Then suppose we search for the phrase guide to Elasticsearch as follows. Based on the analyzed query, the inverted index tells us that both documents contain all three terms. Based on the term positions, we can construct the following. The first document doesn't match because there are two terms in the way, so to speak. The second one does, however, as all three terms appear next to each other and in the correct order. Now that you have seen a couple of queries within diagrams, let's actually run some. I won't cover anything new from now, so feel free to skip to the next chapter if you've seen enough. Anyway, I have 4 simple phrase queries prepared. Let's quickly run them one by one. The first one, which searches for mango juice, doesn't match anything. Let's try the second one. This one searches for the phrase juice mango, which matches one document. The terms are the same, but they are now in the same order as within the document, hence why we get a match. Notice how the hyphen doesn't affect the matching, because it was dropped during the analysis process. That's also why adding symbols within queries won't have any effect either. As you can see, the document still matches despite the parenthesis. Last but not least, let's search the description field for a phrase consisting of 3 words. This query matches one document as well. As we can see, the phrase does appear in the middle of the value for the description field. Those weren't the most interesting queries of all time, I know, but that was just to quickly show you phrase queries in action. That's all for phrase searches. You should now have a solid understanding of how to use the match_phrase query and how it works. That's it. I hope you enjoyed this video on full text queries. If you want to learn more about Elasticsearch, check out my Elasticsearch course. The link is in the description.